Welcome you all to a new session here. Here in this session we are going to deal with sequence detector. Sequence detector is of two types. Now sequence detector is of two types, that is overlapping case and non-overlapping case. Or how overlapping looks and how non-overlap looks under sequence detector, we'll see both the cases. First case, non-overlapping case. Under non-overlapping case, you can observe that I got non-overlapping case, I got the number as 101. Means whenever I am able to detect 1, I need to move from one state to the other state. If 0 is detected, then I need to move from 1 to 0 state. If 1 is detected, then I need to move from 0 to 1 state. Now if you observe clearly my diagram, my state is at S0. When it is at S0, it will remain in the S0 till input is 0 and output is 0. My output will be 1 when complete sequence is detected. Till that time my output will be 0. If 101 is detected, then only output is going to be 1. Now S0 will remain in S0 till input is 0 and output is 0. But when input 1 is occurred, then what happens? S0 state is going to S1 state with output 0. Now under S1, next after detecting 1, my next sequence is 0. Now if 0 is detected, then it is going on to S2 state. But if 1 is detected here, it will remain here only in the S1 state, right? Next, when after going to S2 state, whenever 1 is detected, it will go to S3 state. If it is 0 detected here, then it will go to the initial state. When it comes back to S3, whether it is detecting 1 or whether it is detecting 0, it will go on to initial state, that is S0. Now if you observe clearly, this whenever it is coming as 1, 0 and 1, my output state is represented as 1 by 1. Means my input is 1 and output is 1. Means this is indicating that my sequence 101 is got detected. So this is what related to non-overlapping case. Coming to overlapping case. Now if you observe, this is 101. Now I can take again next series as 101 from here. Next series I can take here from 101. So this is how the overlapping looks like. Here this was non-overlapping case, this is overlapping case. Now similarly, when S0 is going to S1 when 1 is detected, S1 will go to S2 when 10 is detected, S2 will go to S3 when 101 is detected. Now if you observe S0, S0 will come to S1 state when 1 is detected with output 0, S1 will go to S2 with 0 is detected, S2 will go to S3 when 1 is detected with output as 1, that is 1 by 1. Now you can clearly observe that here S1, it will remain in S1 only. Why? Because S1 state is representing one state. That's the reason it is remaining in one state only. If after 1 detecting, if it will go to S1. After that, if 0 is not detected, if 1 is detected, it will remain in S1 state only. So that is the difference between this and that. After that, what happens? After 1 is detected, it has to detect 0. If 0 is detected, it will go to S2 state. If after if 0 is detected, after this particular case, if 1 is not detected, if 1 again 0 is coming, if that is 1 0 0 is detected, then it will go to initial state. Why? Because 1 0 0 is not my series. Now after S2, what happens? Again if S1 is detected, that is 1 is detected, it will complete its sequence, that is 101, and the output 1 is produced. Now after this 0 1 is produced. After this, if my input is detected as 0, it will go to S2. Why? Because 1 is detected, 0 is detected. If 1 comes, it will end its operation here only. But instead of 0, if 1 is detected, then it will go to S1 state. Why? Because S1 state is representing as a 1 here. So this is what the sequence detector does for overlapping case and for non-overlapping case. Let's get on to the next slide. In the next slide, we are going to see about the merger graph and merger table. That is merger method we are going to use to reduce the number of states in the given thing. Now this is merger graph, this is merger table. Now merger method is used to reduce the number of states. To reduce the number of states. Now for example, he has given one problem for us. Now this is our problem. This is my present state, this is my next state with output value. Now next state with the output value for x is equal to 0 and x is equal to 1. So he has given the states this one, A, B, C, D, E, F, G. So he has provided these states for us to represent or to reduce these number of states. How many states are there? 1, 2, 3, 4, 5, 6, 7. 7 states are there. So I need to reduce these states. Now what are those next states? What are its next output values? Everything has been provided in the table. Now these states I need to decrease. Now how I need to decrease? I need to use a merger table and a merger graph representation to reduce these states. How I am going to do? Now you observe clearly. I am writing A to F on my bottom of my table and B to G on my left vertical line I am writing, and I am making boxes individually. Right? I have made boxes individual. After that, I need to compare A state with B state. Means I need to compare these two things. I need to mention whether it is compatible state or incompatible state. How I am going to tell it whether it is a compatible or incompatible? Based upon my output. Means I need to have same output values. Whether it is 0 or 1, both the states should have equal outputs. That is, now if you observe A and B, both states are equal here. So 0, 0, 0, 0. So it is compatible. That's the reason I have written D, E, A, comma, B. So D and E, B, comma, A. So D, E, A, B. These are the two states which are compatible. Why? Because output is equal. Now coming to A and C. A and C, if you observe, this is 0 and 1, 0 and 0, this is 0 and 1. Means outputs are getting differed. So it is not compatible. So I mentioned it as a cross. Next again, what I am doing, B and C. So when I am comparing B and C, 0, 1, not compatible. Next, D and A not compatible. So I am just writing all the incompatible states with cross mark and compatible states with tick mark. Now once I am completing this particular table, what I need to look after? I need to look after again compatible states. Now you check D and E are compatible or not. Now D and E, if I am observing D and E, now both are compatible. That's the reason mark a tick mark here. Next, A and B I need to check. A along with B. Now both are compatible, so I am ticking a mark. So completely I need to mark this particular box as a tick mark. Right? Now next, I need to check for EC, AB. Now E and C. E along with C. E and C, there is no compatible state. So that's the reason I am removing this particular thing. Next, D. D along with E. You can see both are compatible. So I am marking with the tick marks. Right? So once you are done with these particular things, I need to mention my compatible states. These are my compatible states. Now see here, AB is compatible, tick marks. Yeah, I'm just, now this next, D and E, this particular thing, D and E is compatible, D and G is compatible, right? Last one, E and G is also compatible. Right? So I have written all the compatible states here. Once after writing the compatibles, I am just, if you observe DE, DG, EG, means I can write these three states as DEG. Why? Because each and every state is compatible to one another, either the single way or the dual way. So that's the reason I am writing AB, DEG as compatible states. Now I need to write the reduced states. Now reduced states are AB, C, DEG, F. So I was having almost 7 states. Out of 7 states, I reduced the number of states to 5. Now I am considering AB as a W, C as Q, DEG as R, F as T. So I have considered these variables. Now using these variables, I am going to write my reduced table. Now this is my reduced table here, present state with these variables, new variables, W, Q, R, T. Now what is W? A, B, right? Now what is A and B here? D, 0 and B, 0. D means where it is R, right? So that's the reason R, 0. Next B, 0. What is B value? W. So W, 0 I have written. Same output I am writing, but variable I am going to define with WQ. Next Q. What is Q? That is C. What is C here? G, 0 and F, 1. G means R. R, 0. F is T, 1. Right? Next R. What is R here there? R is DEG. So out of DEG, I need to take any one. So A, 1, D, 0. A is W, 1. D is R, 0. Right? Next last T state. T means F. F means C, 0, B, 0. C is Q, 0. And B, 0 means W, 0. So this is reduced table. So after getting reduced table, I have just done a variable representation A, B, C, D, E, F, G. And now compatibles I have marked with straight lines. Now A and B are compatible with DE, AB. F and B are compatible with A, B, and D, E, G both are compatible. That's the reason I have combined them. So this is the merger table, this is the merger graph, this is the reduced table, right? Now let's get into the another topic, and that is ASM charts. Now what do you mean by ASM charts? ASM stands for algorithmic state machine. It contains 3 boxes. One is state box, the other one is the decision box, the last one is conditional box. Now condition box is used only in Mealy machine. Now condition box is used only in Mealy machine. Decision is to take whether are true or false I need to use, and state box is going to represent the state of that particular state machine. Okay, we'll see with an example so that you will understand whether we are going to represent it properly or not. Okay, we'll see with an example. Now I'm taking a state machine called as Mealy machine. For that Mealy machine I need to draw the ASM chart. Now this is the state machine. Now state machine is given with 3 states, S0, S1, S2. S0 will remain in 0. It will go to S1 when 1 is detected. S1 will remain in S1 when 0 input is given. S1 will go to S2 when 1 is detected. S2 will go to S0 when 1 is detected, right? Now for this given state machine, I need to draw the ASM chart. Now if you observe S0, I am taking X as an input value. Why? Because I need to define my input value and output value for X. Now when there is a decision of taking 0 or 1 value, what happening? Whenever it is 0, it is being in S0 only. When 1 is detected, it is going to S1. Now if you observe, 0 is detected, then it is remaining in S. When 1 is detected, I am checking a condition, that is Z value, that whether the output value is 1 or not. I am just checking that value and I am moving that value to S1. Now again here I need to check whether it is 0 or not input value. So I am taking a variable X with 0 and 1. Now if you observe clearly, when 0 is detected, the output is 1 here. So whenever the output is 1, I am taking this Z value, that is output value Z as 1. Why? Because output is 1 here. So that's the reason this output Z I am mentioning for 0 value, and which is going back to S1, here. Now when 1 is detected, what happening? It is moving to S2. So whenever it is 1 is happening, it is going to S2. Again after coming to S2, I need to check the condition for X 0 and 1 value. Now if you observe 1 for 1, output is 1, it is going to S0. For 0 it is remaining there. Now for 1 and 0 if you observe, now for 0 it is remaining in S2. But for 1 what happening? The condition is output as 1. So that's the reason I am drawing a conditional box with output Z, and it is moving to my initial state S0. So this is how you draw ASM chart for any kind of given state machine. Now state machines, you know, with the help of state diagram itself, we can tell that this is a Mealy machine. Similarly, the state diagram we can also represent for Murray machine also. How Murray machine looks? If you observe clearly, this is Murray type of machine. Now this is Murray type of machine. You observe clearly here, the state is mentioned with a state by output value. This is state with output value, whereas on transition signals it is mentioned only the input values. Now if you observe clearly, 0 by 0, this is 1 1, 0 1 1 0, 0 1 1 0, 1 1, 0 0, 1 1, 0 1 0 1. So I am giving a task for you in this session, that for this particular kind of machines you need to draw a ASM chart representing the proper conditions for this particular state machine, so that you are going to get appropriate ASM chart for this. Okay, let's end our session here. Thank you one and all.